Good morning, everyone. I'm honored to be here to present our recent work to you. My name is Wenzhen Huang from Chang'an University, located in Xi'an of China. My topic today is about under ice dissolved oxygen and metabolism dynamics in an arid region shallow lake, the critical role of ice and snow. And I have to say, this work is jointly done by many authors, including Professor Zhijun Li from Dalian University of Technology of China, and Professors Marty Labranta, Laurie Avila, and Jussi Hoteri from University of Helsinki, and other two scientists from China. Why we put ice on dew in ice-covered lakes? As we know, more than half of the world's lakes are seasonally ice-covered, and an ice and snow-covered lake is remarkably different from one with an open water surface with respect to the optical, thermal, and mechanical properties. Freezing of lakes brings a divergent seasonal aquatic environment compared with the open water period in terms of lake physics, chemistry, and ecology. Generally, the ice and snow cover makes the under ice water cold, dark, and relatively calm. But the life under ice is still colorful and active. For example, the under ice biomass is comparable to the warm seasons in this lake. But the phytoplankton and the zooplankton groups, community structures, are quite different with warm seasons. But what drives these changes? We still don't understand clearly. And due to climate change, shortening of ice cover duration and ice thinning has occurred worldwide in the recent decades. In particular because climate warming has been pronounced in cold and high mountain regions. So we got a question: what's its impacts on the limnology in this area, in these regions? It is believed to change the lake mixing regimes, generally from digmictic to monomictic, and stable stratification and bottom anoxia duration become longer. It is also to believe that we also believe that the changes in ice cover can cause change in ecological and biological processes in cold region lakes. For example, Griffiths in his article concluded that the length of ice-free season is the principal driver of diatom assemblage responses to climate in the high Arctic, largely driven by the establishment of new aquatic habitats, resulting in increased diversity and the emergence of novel growth forms and epiphytic species. But if we want to accurately evaluate the impacts of the ice thinning and shortening on limnology, we can easily go to a key question. That is, how does the lake ice interact with on-ice water and further drives habitat and ecological evolution? But if we look at this picture, we will realize that it is not easy work to find answers to this question, because there are a great number of physical, chemical, biological processes influencing the air-ice-lake system. It covers many subjects, including climate change, boundary layer meteorology, ice physics, lake thermodynamics, like hydrodynamics and hydrogeochemistry, biogeochemistry, and aquatic ecology, and other scientific subjects. This is a quite complicated system, and it's not easy to find for us to do the question. But I think we have to start somewhere. As an ice scientist, we can easily go to the dissolved oxygen because it is a good indicator of the ecological status of aquatic habitats and plays an important role in many chemical and biological processes. For example, with an extremely lower dissolved oxygen or anoxic layer over the sediment surface, toxic compounds and greenhouse gases can be produced, such as methane. Generally, in Arctic, Boreal, and Central Europe, the maritime climate brings a lot of snow in winter, so the snow can accumulate on the lake ice surface. The thick snow layer can cut off the light that penetrates into the on-the-ice water, so the on-the-ice photosynthesis processes can be ceased. The dew have to deplete continually due to the water and sediment oxygen consumption, and usually bottom anoxic layer can develop and sustain. In China, 74% of lakes are located in seasonally or permanently frozen zones, and these frozen zones overlap largely the arid and semi-arid regions. So I mean the cold arid regions. As we know, the high mountain area is featured by these cold arid regions. In these regions, we usually have dry air, more solar radiation due to the lower latitudes, and little snow in winter. This can create bare ice surface. And also, lakes in these regions are somehow euphotic. So we got a question. We don't know what is the difference in lake dew dynamics during ice seasons in these cold arid regions compared to the maritime climate dominated regions, and what is the role that the ice or snow cover plays in dew evolution. With these issues, we conducted couples of years of field observations in the lake in typical cold and arid region. This lake is called Wuliangsuhai, located in Inner Mongolia of China. It is in an arid or semi-arid region of South Mongolian Plateau. It belongs to temperate continental climate. The triangles in the picture showed our field sites in this lake. This lake is featured by a small annual precipitation and large evaporation. It has an altitude of over 1,000 meters. The annual air temperature in this lake area is about 5 to 7 degrees centigrade. And this lake is the 18th largest freshwater lake in China, but it has a very shallow depth. Its mean depth is about 1 meter. In this lake, the lake freezes up on early December and breaks up usually on early April. The maximum thickness of ice occurred usually on late February. It is about 40 to 60 centimeters thick. In this lake, there are a lot of emergent and submerged plants. about 60% of the surface area is covered by dense beds of reeds, and the rest is open water. And this lake is middle to highly euphotic, especially in winters, with high level of chemical oxygen demand, total nitrogen, and total phosphorus. In the sites, we used thermistor chain to observe the air, ice, water, and sedimentary temperature profiles. And we use dual sensors to monitor the dissolved oxygen concentration in the water column. And we use trio sensors to observe the incident, reflected, and transmitted solar radiation, mainly in the PAR band. We also established an automatic meteorological tower to monitor the weather conditions. With 3 winters of observations, we got high-frequency datasets. And this picture shows the field setup of all apparatus and the main observed factors. With 3 winters of observations, we got high-frequency data of ice thickness, air, ice, water sediment temperature, dissolved oxygen in water column, and the total incoming and outgoing radiation, and also the under ice downwelling and upwelling irradiance. So with this datasets, we can get some direct results. First, let's look at the snow and ice condition. We have to admit that all the 3 monitoring periods covered only the midwinter season, when the ice was in transition from growth to melting, and reached its maximum annual thickness on middle February to early March. And due to the arid climate, only 4 small snowfall events occurred over the 3 observation seasons. A 4 to 6 centimeters thick snow cover formed and stayed roughly for a week, and then disappeared due to the thermal and wind-blowing ablation. The rest of the time, the ice surface was consistently free of snow, or only covered by patchy snow thinner than 1 to 2 centimeters. If we look at the time series of the DO and temperature, we can see that during the entire cycles, in both water temperature and DO, were observed throughout the 3 winters, mainly because the bare ice surface allowed transmission of solar radiation into the water column that can drive the DO and the temperature change. But one thing we have to notice is that even under clear sky, snow cover can diminish or even cut off the dial changes in the water temperature and DO. So maybe we can say the daily amplitudes of DO and temperature showed seasonally variation largely due to insolation and snow events. If we look at the thermal structure of this lake, we can find that an inverse thermal stratification usually persisted throughout the ice season, and the temperature can reach up to 6 to 8 degrees centigrade at the lake bottom. And in particular, near the onset of melting or even during the equilibrium stage, an isothermal layer appeared in the middle layer in the water column, and gradually deepened to the near bottom layer in winter 2018. and the bottom anoxia, and the dew profile presented a reverse structure compared with the temperature. Dew was high in the topmost water layer and reached its minimum at the surface of the sediment or anoxic layer. And the bottom anoxic layer developed during winters 2017 and 2018, but only a transient, thin dianoxic layer formed in winter 2018. And this figure shows the seasonal variation of water temperature and the DO. We can see that DO and water temperature had quite similar diurnal and seasonal patterns. Especially when the ice surface was snow-free or covered with very thin snow, the midday bulk oxygen concentration was usually 0.5 to 1.7 milligram per liter, higher than those in early morning. When a snow cover was thicker than approximately 4 centimeters, diurnal changes in dew concentration disappeared, and the dew continued to be depleted due to water and sediment oxygen demand. For instance, between February and February 8 and March 3rd in the winter 2017. This may indicate that snow cover was the first order factor impacting their seasonal variation. So here, directly from the observation datasets, we can get some short summaries. 1. The under-ice water was warm, and the bulk dissolved oxygen concentration was high in midwinters in these lakes. 2. During the diurnal cycles in both water temperature and DO were observed, especially under clear sky with no snow covers. 3rd, an inverse thermostratification usually persisted throughout the observation, but convective mixing occurred in winter 2018. 4. DO was high in the topmost water layer and reached its minimum at the surface of the sediment or anoxic layer. 4. Snow cover may be the first order factor impacting their seasonal variations. But the question mentioned at the beginning has not yet resolved. We need to understand how to relate snow and ice condition with dew variations, so we have to resolve some little questions. First, can oxygen be excluded from ice to water during freezing? Yes, according to our observations, it is yes. Oxygen can be excluded to water during freezing, just like salt exclusion. Then we can decouple dew dynamics into gross photosynthesis production and respiration. Here, the respiration includes the water and sediment oxygen consumption. If we can get the GPP and R rates, then we can investigate the relationship between GPP and solar radiation, and the relationship between R and the temperature. And we all know that the solar radiation and the water temperature is influenced by the ice cover. I mean the ice freezing and melting. Then we developed a model for dew transport at the ice-water interface. When the thick of ice changes, the mass fluxes of oxygen and water per unit area to the water column can be derived from the two equations below. And according to the observations of dew concentrations in ice and underlying water layer, we can estimate dew and water mass flux through the ice-water interface, according to these two equations. Actually, in ice growth, the capture of oxygen is described by the segregation coefficient gamma. Here, we assume that the segregation coefficient is constant and that there is no advection of oxygen in ice. We take gamma equal 0.15 based on our sampling data. Then we can calculate the oxygen and water mass fluxes through the ice-water interface over the observational period, just like this. This figure shows the results. Next, how to estimate the metabolic rates. Actually, we modify the free water dew series method to calculate the GPP and R according to dew time series. Free water dew series method has been widely used to estimate the metabolic rates based on the evolution of the dew concentrations with time. If we assume that transport and all dew sources and sinks other than gross photosynthesis production and respiration can be neglected, the change of dew concentration equals the net ecosystem production. This can be expressed in this equation. Actually, in ice-covered lakes, vertical diffusion and convection take place in the water column, but their impacts can be removed when the above equation is integrated through the entire water column. And then, by adding the impact of oxygen exclusion during freezing and dew dilution during melting, and also assume that the chemical and sediment oxygen consumption is included as a part of the lake ecosystem respiration, for the sake of simplicity, then we can get this equation. The first term denotes the change of the dew amount in the whole water column. The second term denotes the net production of dew by photosynthesis and respiration. The last term denotes dew exclusion or release from freezing or melting processes of the water. From this equation, during daytime, we can separate the time into daytime and nighttime. During daytime, the difference of dew amount at two consecutive times can be expressed as the middle equation. And during the nighttime, there is no photosynthesis, so the middle equation can be transformed into the last equation, which deleted the GPP. So since we observed dew concentration changes in nights, we can get nighttime respiration R from the last equation. Then, since we assume the nighttime respiration equal to the daytime respiration, that means in the middle equation, the daytime R is known. So with the daytime DO observations, we can calculate the GPP in daytime. Then, with the estimated GPP R and observed PAR transmission and water temperature, we can see, and this picture shows the on-ice lake ecosystem metabolic rates according to the above modified free water DO series method. We can see that the GPP and R were highly correlated, and their values are higher than previously reported values in other lakes. For example, in Arctic, Boreal, and Central Europe lakes. And also we can see that the GPP is positively correlated with PAR and water temperature. And we can say PAR is one of the key drivers for GPP. But physically, PAR transfer is controlled by the ice and snow conditions. According to our estimation, over the 3 winters of observation, 35%, 39%, and 26% of the incident solar radiation was reflected by, absorbed, and transmitted through the ice-snow cover during 3 winters. But snow cover provides a very negative effect on light transfer. For example, when a new snow cover thicker than 4 centimeters formed, reflection, absorption, transmission changed to 79%, 17%, and 3% respectively. And consequently, the concurrent GPP dropped to 20% to 25% of the level before the snow event. If we consider the euphotic zone, here we use 12 as the threshold to define the euphotic depth. Then we can get that the snow and ice cover took up more than 30% of the euphotic zone, and the ice and snow cover also shortened its duration by 1 to 2 hours each day. And we can also see the bulk water temperature followed clearly the daily and seasonal variations in penetrated radiation. The variation in penetrated radiation can account for 60% of water temperature variability. So in this way, we can say the ice and snow processes can play a critical role in the on-ice DO dynamics and also the metabolic rates. Now we can go to the conclusion. In mid-latitude cold arid lakes, diurnal and seasonal variation in DO and water temperature was observed, largely attributed to cycles in solar radiation. In this lake, higher oxygen production and consumption rates than previously reported. The high oxygen production and consumption mainly resulted from the higher higher trophic levels, and the shallow depths of the lake, and most importantly, from the higher on-ice solar radiation and water temperature. And in this work, we find three principal ways the ice snow cover influences on-ice dew and metabolism. The first, the thickness and optical properties of ice and snow cover controlled the light transfer and the depth of the euphotic zones. Second, the ice and snow mediated radiation and ice-water heat transfer controlled the water temperature, or mainly influenced the water temperature. 3. Dew exclusion during freezing and dilution by meltwater can directly change the dew concentrations in the topmost water layer and also change the total amount of oxygen in the whole water column. That's all. Thank you.